Hi, thanks for having me in the CUDA community meetup. Before I got started, I wanted to just briefly introduce myself. So I'm Graham Markle, and I'm a software engineer in the Rapids team at NVIDIA, where I mainly work on maintaining Numba and supporting it being used in QDF and other Rapids libraries. So I've been at NVIDIA for a couple of years now, and I'm still enjoying myself here. Generally, here and in the past, I've focused my career around the intersection of compilers and numerical methods and accelerated computing, mainly because I like trying to make powerful software tools accessible to as many people as possible, which is what I'm trying to do with Numba as well. So what is Numba? Broadly, I think there's two different useful ways of thinking about it. One of them is that it's a compiler that can translate Python code into CUDA code so it can run on GPUs. And then another way of thinking about it as well is that it's a tool that you can use to connect together all the different libraries and applications in the CUDA Python ecosystem. And I think of both of these aspects of it as being quite important, because in the long term, I'd like it to be as natural a choice to write code for CUDA GPUs in Python as it presently is for C and C++. So just before I go any further into the talk, let's just see where we're going. What I'm aiming to do is just give a fairly broad overview of as many Numba related things as I can, rather than a deep dive into any one area. So we'll start with an overview of Numba, how to use it, and a bit about how it works. Then I want to talk about some examples of libraries that are using Numba, and then to discuss how some of the standard CUDA tools can be used in conjunction with Numba. There's a bit of extra material I've got as well, which I probably won't have time for today, because this talk is condensed down from a much larger tutorial on Numba, but there's that extra material if we've got time for it. So looking a bit closer at what Numba is, if you were to make a headline summary of it, it's a just-in-time compiler for Python functions. And when you want to use it, you don't compile an entire Python program. You just opt into using it for the specific functions that you want to accelerate. And the kinds of functions that it works best with, especially for the CUDA target, tend to be those that are fairly numerically focused, with large arrays and lots of data. It doesn't support every single Python language feature and library. We'll have a look at a bit more about what's supported later. But when you use Numba, you're essentially making a trade-off. You're working with a limited subset of Python in return for much better performance. You could avoid using Numba by rewriting your Python code, maybe as CUDA C or C++, but sticking with Numba gives you a way to use CUDA whilst keeping all your source code in Python. It's not just a CUDA compiler, though. It targets CPUs and GPUs. The CPU targets had most of the development effort go into it, and but we are spending a significant amount of effort on CUDA development for it these days as well. It did also have an AMD GPU target, but unfortunately that didn't get as much maintenance and it bit rotted, and that target was eventually removed. So why use Numba and keep everything in Python instead of just taking the alternative route and rewriting performance critical sections in CUDA C? One reason for that is that the PyData ecosystem is quite strong and well developed, and that's an ecosystem that facilitates lots of scientists and engineers and software developers who are people who are maybe working with numerical methods or machine learning or AI applications that are used to doing all their work efficiently in Python. So if you keep all the code as Python code, it's much more within the comfort zone of that kind of community. So it makes it easier for those kinds of users to focus on their algorithmic development instead of having to master or learn another technology like C, C++, and CUDA. Kind of helps to maintain the interoperability that that ecosystem already has. So who are these people using Numba? So a little while ago, I pulled these numbers from PyPI and Conda in GitHub. I don't know too much about how I would go about interpreting these numbers, but I think they should be convincing in showing some way that there's a large enough number of people using Numba that it's generally interesting and useful. I have done in the past, various searches for applications that are using Numba's CUDA target. Some of the interesting examples are listed on the slide. There's a link to a GitHub repository where I keep track of a few other users as well that are also on the slide, which we posted a link for. In terms of development, most of the time we're getting by with a fairly small team. There's 4 developers in the core team, 3 are at Anaconda, and there's myself at NVIDIA. We do get some extra effort from some other developers in NVIDIA at the moment as well. But mainly, there is a long tail of very small contributions that have been made, maybe 1 or 2 people who make 1 or 2 PRs and then that solve their need and then kind of move on, and then a few formal contributors as well. So it makes it look really busy, like there's loads of contributors, but most of them are just fairly small contributions. Okay, so let's dive into the API a bit to look at what it's like for a Python user who wants to run their code on a GPU. So on the left, we've just got a simple function that adds 2 vectors together. And then on the right is the version rewritten to run on the GPU with Numba. So from the user's perspective, what they had to do was to add the CUDA.JIT decorator to tell Numba to compile the function, and then replace that for loop with a grid-strided loop that's more kind of idiomatic in CUDA C and C++. Then they can launch the kernel with this kind of syntax. So we have to use square brackets in Python for the launch configuration, just because there's no way to support the kind of triple angle brackets that we have in CUDA C and C++. But then after that, the parameter list comes as usual. So in this case, these arrays are X and Y. They could be a NumPy array, or they could be some array on the device. Before we go a bit more into Numba itself, I did want to draw attention to some of the slightly relevant differences between Python and C++ that I kind of think help make sense of why things are the way they are in Numba, which might be helpful if you're not so familiar with Python. It's not a hugely exhaustive and detailed comparison, but just kind of to give an idea. So first of all, typing, kind of Python's typing is fairly sort of loose. Any type of object will be accepted anywhere, as long as it supports the right operations and members in the context in which it's being used. I think the nickname is duck typing because its objects are sort of treated like, if they quack like a duck, then they're a duck, or can be used as a duck. You also don't have manual memory management in Python. Instead, allocation and deletion is automatic, and objects get garbage collected when they've gone out of scope in all namespaces. You don't usually also compile Python code ahead of time. When you run it in the interpreter, it gets compiled to bytecode and interpreted, but that compilation to bytecode is transparent to the user. This kind of contrasts with the compilation and linking process that you would normally have in C and C++. Also, it's quite common in Python for a developer to work at an interactive prompt, typing in statements and then executing them, and particularly if they're sort of exploring or working with a new data set. When it comes to actually writing the kernels in Python versus writing them in C++, though, there isn't really too great of a difference. I've got a C++ kernel on the left and the Python equivalent on the right. This example is taken from the SDK example, so there's some reduction using a cooperative group. You can pretty much see the one-to-one correspondence between items in the C++ and Python, so you don't really have to change your thinking too much, or change the code too much for Python as such. In terms of what CUDA features that we actually support in Numba, what we've aimed to do is to cover as many of the CUDA features as possible. Not everything's there, but quite a lot of the commonly used things are there. So we support all the different kinds of memory, intrinsics for things like indices and atomics, a little bit of cooperative groups, streams and events are supported, and the profiler APIs. And there's also an API for compiling Python functions to PTX so that you can compile Python and use it elsewhere, maybe linking it to some other code from another language. If you are using Numba and you find there's a CUDA feature that's not supported, some things are missing because they're difficult to implement, some things just because they might have been overlooked or not requested yet. So if there's a feature you'd like to use in Numba, you can always raise an issue on the issue tracker to request something, and we'll see if we can add it. In terms of Python features that are supported, I did mention that it's only a subset of Python that's supported. So inside a function that you decorate, the syntax that's supported is all the typical sort of expressions, basic control flow. You can raise exceptions and you can use assert as long as you're in debug mode and calling other functions that have been compiled as well. That's kind of a summary, but there's a link to the documentation on the slide of everything that is and isn't supported. What does that leave in terms of syntax that's not supported inside JITted kernels? You can't handle exceptions, so you can't catch them with try and except. There's also no support for context managers, so you can't use the with statement or generators, and comprehensions like list and set comprehensions aren't supported. You also can't decorate a class with CUDA.JIT. You can do some JITting of classes with Numba's CPU target, but that support's also a bit experimental. The documentation also enumerates some of the built-in features and types. There's a few listed on the slide, but the documentation goes into detail. So the usual sort of mathematical types and built-in functions are there. In terms of supported Python modules, from the standard library inside the CUDA target are the maths and operator libraries. Again, more comprehensive list in the documentation. The other main module that we aim to support is the NUMPY module. So it supports all kinds of NUMPY arrays of scalars and structured types, except arrays that contain Python objects. They can only contain sort of numeric values. Attributes on those arrays, like the shape and the strides, you can index arrays and slice them. So it's kind of easy, relatively easy to manipulate the shape of things. Date times supporting in kernels, and then some of the scalar NUMPY functions that accept a scalar and return a scalar are supported as well. What does that leave? That's sorry. So there's a little bit more I'm going to talk about NUMPY a little bit later down when I talk about that in a few slides down. But for now, I want to spend a little bit of time looking at how Numba works. So there's two reasons for doing this, and one is that I think it's interesting to look beneath the hood and see how it does what it does. But I also think it's helpful to know what it's doing to really be able to use it effectively, so that you can help work out what's happening when things go wrong, or why things might not be as fast as you were hoping for performance optimization. So in Numba's CUDA target, you can break it up into three main components, and the first is, which I'm mainly going to talk about, is the compiler, which takes Python and emits PTX using NVVM when you use the CUDA-JIT decorator. There's also a wrapper for the driver API, which can use some C-types bindings that Numba has built in, or it can use the official CUDA Python API. And then the third component is a NUMPY-like device array library, which gives you some NUMPY-like operations, but generally what I tend to recommend people do if they can is use CuPy arrays instead, because they can be used transparently with Numba. Anyway, let's mostly look at the compiler. So we'll try to start from the top down and have a look at what Numba does when it compiles a function. So when it has to compile, it's going to take the Python code of the function, and the aim is to transform it into LLVM, intermediate representation. And then it will use the LLVM library to generate assembly code for the target hardware, which could be something like x86 or ARM or a GPU PTX. So if you haven't come across LLVM before, it is a fairly widely used compiler infrastructure, and it's got support for lots of different targets and lots of different optimizations built in. So it makes it comparatively easy to write a compiler, because you've only got to write a language front end that generates the LLVM IR and then let it do the optimization, the code generation. A lot of the heavy lifting that you would have had to do to implement the compiler is done for you. So it's quite popular. A lot of tools use it. Next, let's have a bit more look in detail at the pipeline that takes Python bytecode and eventually produces LLVM IR. So this is what the pipeline looks like. Assuming we had decorated this function ax plus y with the CUDA-GDB decorator, it gets called and then Numba's got to compile a version of the function. The first thing that Numba will do is take the code of the function and use Python's bytecode compiler to turn it into bytecode. And then it runs a step called bytecode analysis that translates the Python bytecode into Numba intermediate representation. The reason that it does that is that it needs to do type inference on the function. So Numba's intermediate representation is a bit easier to do, or more designed for doing type inference than Python's bytecode is. The purpose of type inference is to figure out what the type of every variable and value and intermediate expression in the function is going to be. And to start that process off, it's going to use the arguments to the function. So if it's called with R, A, X, and Y, it takes the function arguments and looks at what the types are, and that goes into type inference. We'll have another look at type inference in a few minutes, but for now, we'll just assume that the type inference stage has figured out what the types of everything is. Why did it assign a type to everything? The reason is that although Python source code has got no type information, in a low-level language, like eventually the assembly code is going to have a type for every single value and instruction. So that once we have the typed number IR, we can then translate that in the lowering stage to LLVM's intermediate representation, which is a fairly sort of mechanical translation process. Once we've got the LLVM intermediate representation, we then pass it to LLVM's JIT compiler. In the case of a CUDA GPU, we use NVVM, which is NVIDIA's based on LLVM for generating PTX code for CUDA GPUs. So after it's been through the LLVM or NVVM JIT, we've got machine code that we can either execute or we can put in a cache for later, because we don't want to recompile the same function over and over again. So just to summarize, the compilation pipeline, it takes the Python bytecode, builds an intermediate representation, figures out the type of everything, lowers that into LLVM's intermediate representation, and compiles it to machine code. When does that process start to begin? It happens when if you've decorated a function with the CUDA.JIT decorator, when that function gets called, the numbers dispatch process is what's going to kick off the compilation. So upon the time that a function gets called, Numba is going to inspect the types of all the arguments. And then before it kicks off that compilation pipeline, it's going to check, are there any compiled versions of the function in the cache that already match the types of these arguments? If so, it can retrieve the compiled code from the cache. If not, then it will kick off the compiler pipeline. Once it's got to step 3, we've got some compiled code, but what it's being called with is some Python values. So it has to do some marshalling where it unboxes the Python values into native values. Then it can call a native code function on those native values, maybe with some and then after the function returns, if there is a return value, maybe box the return value back up into a Python value. If we're dispatching a CUDA function, there's a little bit more work to do. because we don't just interact with LLVM, but we also then pass that LLVM IR to NVVM to get PTX back. Then it uses the driver API to link the module and load the module as well. Next, if any of the arguments were in host memory and not device memory, then it has to transfer data to the GPU before it then packs the arguments into an array and launches the kernel through the driver API. Oh, right, yes. I just want to check if there's any questions at this point, because I know I've gone through quite a few things, just if anything needs to go back and be clarified at the moment. If so, I'll check the chat again in a couple of minutes, just in case. I mentioned a bit earlier about the type inference phase, and that needs to be done. So what I'm going to try to do here is walk through the process a little bit more with this example code. So as I mentioned, there's no type information in the Python source. And the way type inference works is that Numba propagates the type information from the arguments all the way through the function to all the return points in the function. So it uses that, or it does that by following the data flow through the function. Then every time some kind of operation or function gets encountered, it's got to figure out using what the mapping is from the input types to the output types. So if we've got this function that adds together two, let's say, integers. If we assume it was called where A is a float 32 and B is a float 64, that would propagate to this addition operation. Then we have the addition is operating on a float 32 and a float 64. So Numba's got, what number we're trying to determine is what's the type that I can use to represent the result of this in the most exact way possible. And one way to do that will be to use a float 64 for the result as well. So the data flow into C would propagate a type of float 64 to C as well. Propagating again to the next line, the value C is returned. So the return type of the function would be the same as the type of C, which is float 64. Now this example is just sort of straight through the function. It's a little bit more complex when there are branches and you have values coming in from different branches that Numba has to work to unify them together as well. But I'm going to skip over that for now. That kind of explains all the sort of different pieces of the pipeline at a high level. I wanted to talk a little bit about the device array library as well, mainly because that helps to talk about memory management a little bit. Because, like I say, I generally recommend that you use CuPy arrays if you can. But let's have a look at Numba's device array library and NumPy. So NumPy is the fundamental, in a way, the fundamental building block of numerical computing in the PyData ecosystem. Just in case there's people who are not familiar with it, I thought we'd take a quick look at it. I'll come back to that question in a second. It's a Python library that gives you a kind of convenient way of working with n-dimensional array objects and lots of functions for operating on those objects. It also, importantly, defines an interface for getting at the data of the array and for wrapping up data from elsewhere as an array, so it kind of provides an interface as well. There's a couple of really simple examples using NumPy on the slide. So one shows how you can create an array object, for example, with a range, and then manipulate it element by element by writing expressions that are fairly similar to the form in which you would write them down. So here we've got this array X of elements, and then we multiply all the elements by 2, and assign the result back. There's lots of functions NumPy provides that operate on elements as well. Like, for example, the cosine example here. Just before I carry on, I'll just check what that question was. What if another line says C equals strc? What will the type be inferred for C? The question about typing was, what if there's another line saying that C is a string? I think I could spend a few minutes getting into the details of type inference a bit deeply. So what I'm going to do is come back to that question at the end, and I can talk in a bit more detail about type inference. Sorry about that. Oh yeah, so not every NumPy function is supported on the CUDA target. For example, you can't create new arrays inside kernels. That means that some NumPy functions that return a new array also can't be used. So for example, you can't use a function that takes an array because that's going to return you a new array. Some other array methods are also not yet supported as well, like something like that computes the mean of the arrays. What I'm hoping to do is increase that coverage with some changes in the CUDA target in the next release of Numba, which is probably expected around May or June 2022. Sorry, that's this year, isn't it? Yeah, May or June. Okay, so we're going to have a look at memory management and number device arrays with a couple of examples. So here's an example where we've got a JITted function that takes two vectors, x and y, and then it adds their elements, and then it stores the result in another vector. If we create some NumPy arrays that are on the host, and then we call this kernel, then Numba is going to automatically determine that it needs to transfer those arrays to the device before it calls the kernel, and then transfer the result back, or transfer R back after it's executed. And that's kind of convenient if you're just developing the code, because it saves you doing any work to copy things, but it's not particularly efficient because in most cases you're going to want to manually manage the transfer and creation of arrays that are on the device. So what we do instead in this example is to transfer the X and Y arrays to the device ahead of time. It doesn't really matter what the contents of the R array are going to be, so we just create one on the device that happens to be the same shape as X. Then when we launch this kernel on these arrays, Numba's going to recognize that these are all device arrays and there isn't a transfer. We don't need to invoke a transfer. If we do want to get back at the results on the host, we can use the copy to host method to get a NumPy array back. You also don't need to have an array on the host to be able to create one on the device. You can just use the device array constructor and give it something like the shape and the data type that you want to create. So here we're creating a matrix of float 32 values. That's how you allocate memory on the device. But what about deallocating or freeing it on the device? Because as I mentioned a little bit earlier, there isn't really an explicit freeing of Python objects. So there's no direct way you can tell Numba free this array. Instead, it handles the deallocation by freeing the underlying memory for device arrays when the device array object that refers to it gets garbage collected. So objects tend to get garbage collected when there's no references to them in any namespaces. You can remove a reference from the current namespace using the del operator like this. So in this example, if we deleted dr and then there were no other references stored anywhere else, Numba's going to mark that underlying memory as ready to be freed. And then next time Numba does some cleanup, it'll be able to free it. So cleanup is a bit of a complicated topic. And there's some documentation of the exact strategy that Numba uses on the in the documentation linked on the slide, and some general memory management documentation as well. So that sort of covers memory management. The next area I wanted to go to was to talk about a few notable libraries that use Numba for CUDA And one reason that I'm doing this is sort of in lieu of presenting extensive benchmark results, because one way in which I'd normally like to be able to justify the usefulness of Numba's CUDA target would be to provide some rigorous and exhaustive benchmark suite and results that compares the performance between CUDA Python and CUDA C++. Unfortunately, I just don't have anything comprehensive in terms of benchmarks for that kind of thing to present. So instead of that, what I want to do is kind of show some interesting use cases that people have for Numba that I think justify its performance is sort of significant enough to make it a useful real-world tool, at least. So STUMPY, or STUMPY is the first one, which is a tool used for computing the matrix profile. And that's this is quite a computationally intensive operation. Typically, it gets used for runs on large data sets that can take hours or days to compute. There's a lot of applications that are listed on the slide. I've just taken these straight from its README. In terms of performance, my understanding is that it's regularly used on GPUs, and it's been benchmarked in a variety of different configurations and GPUs that show favorable performance compared to a reference implementation. This example I took again straight from the README on the GitHub repository, and there's more details about that in the linked repository. The second example is two of my colleagues at NVIDIA wrote about a complex application that's got Numba right in the middle of the workflow, and that was published on the NVIDIA developer blog. This is an application that ingests and processes data using a variety of steps, and the majority of those they're all done on GPUs. The majority of those steps could be done straight from Python using standard libraries like UDF and CuPy, PyTorch, qcrossfilter. But there's one step specific to this workflow that needed a custom kernel, which Numba was used to write, and that in doing that, that meant that they could keep all the data and operations on the GPU and therefore maintain high performance of the whole pipeline. Again, there's a link to the blog post in the slide, more details on there. The final example I wanted to draw attention to is the Rapids QDF library. So this is a CUDA library that provides a library that uses CUDA that provides the same functionality in Python as the Pandas data frame library does for the CPU. And one of the requirements for the Pandas API is that users should be able to write their own functions in Python that then get applied to data frames. So what QDF does is to use Numba to take users' Python functions and compile them, and then it can launch those compiled kernels on the GPU data frame. So in this example on the slide, the user writes in Python something that takes in a row, adds together the elements of the row, and then filters the output based on the sum, returning either NA or some value. So they write this function. At the point in which they call apply of the function on the data frame, this is when QDF would take that Python function, compile it with Numba, then apply it to produce the result data frame, again, with all the computation happening on the GPU. This example is one I've just taken from the Rapids Guide to UDFs that's linked in the slides, but there's various other use cases for this, applying UDFs in different ways. So those were the examples. Kind of for the last section of the talk, I wanted to go over some of the development tools that you can use in conjunction with Numba. The reason that I'm interested in supporting these is that I think it's important that we give a sort of complete development experience for writing CUDA kernels in Python to make it as easy as possible to debug and to optimize CUDA Python kernels. One thing you can do to make it a bit easier to debug a kernel is to pass the debug equals true keyword argument to the CUDA-JIT decorator. And that does two things. The first thing it will do is it will turn on checks for exceptions being raised in your kernel, so including assertions. So if you use debug equals true, that means you can raise exceptions and use the assert keyword in the kernel. Secondly, it adds line number information to the generated code. So that makes it a bit easier to interpret what's going on in GDB or CUDA-GDB when you're debugging. And it can also make it a bit easier to locate problems if you're using COMPUTE-SANITIZER with CUDA Python. So I've got some examples of using these over the next few slides. So in this example kernel, it's mostly correct, except there's an off by one error. In this line, we're not checking the bounds of the array correctly. We're going to access one element beyond the end of the array. If we ran this kernel without debug equals true, it will probably run to completion, but it would overwrite one element past the end of the array. Whereas with debug equals true turned on, we'd expect to get an exception raised because we went out of bounds. You could also track this kind or spot this kind of thing using COMPUTE-SANITIZER with Numba. The memcheck tool I find works generally quite well with CUDA Python code. I tend to use it on a regular basis when I'm debugging either my own code or maybe other people's bug reports or Python kernels. This is the same example. What you would see if you ran this on the COMPUTE-SANITIZER is that there's an invalid read. It's able to give which thread did the out of bounds read. It can also locate the let's move that. It can also locate the Python source file and source line in which the error occurred, the name of the function in Python. So it gets mangled to CuDaPy main add one, but we can see it's the add one function and the types with which it was called as well. So it can be useful to kind of quickly pinpoint where problems are coming from in Python. You can also use CUDA-GDB with Numba kernels for some limited debugging features. You can use CUDA memcheck in conjunction with CUDA-GDB so that it will stop whenever you get a memcheck error. You can set breakpoints on kernel launches. You can step through them by instruction, and you can view the source corresponding to where you are as well. There are a couple of other limitations, which is that you can't backtrace through the host code, so it can be tricky sometimes to see where your kernel got launched from if you're having an issue. And sometimes stepping my source line can not always behave reliably yet. Here's an example, a quick example of a session. In this example session, what I'd done is set CUDA-GDB to break on the kernel launch. I've just hit my first breakpoint, line 12 of repro.py. If I do list, the view you get in CUDA-GDB is that of the Python source code that you're running. Then I've also got decided to list the disassembly in this example. A little bit of a further example, this time using CUDA memcheck when the program's run. I think this is our add one off by one error from earlier. It will break. We see that it breaks when you get to the illegal access. This demonstrates kind of the limitation with the backtrace I was talking about. It only goes through the stack on the device. You don't get a backtrace through the host to see where that was coming from. You can also disassemble the code, the SAS code. If we step a couple of instructions, we would then see that we've moved on a couple more instructions. So it's probably not as rich the CUDA-GDB as experience as you would get with CUDA C++, but it is a tool that you can use to try to learn a little bit more about what's happening if you are having problems. So CUDA-GDB is quite a low-level tool, and it can also be hard for some users to use just because they're mostly versed in using Python rather than tools like GDB. So we've also got a CUDA simulator that you can use to debug your kernels using the Python debugger, or anything that runs on top of the Python debugger. So this screenshot is of me using PUDB, which is my favorite Python debugger. The way the simulator works is similar to the way that the original CUDA simulator that came with early CUDA toolkits used to work, where we launch a lot of threads on the CPU and then we switch between them. And it kind of has the same issues of performance and faithfulness to the device's semantics that the original simulator had. Ideally, what I'd like to do is make the CUDA-GDB support work well enough that we could retire this CUDA simulator, but we're not there yet. I've also seen that some users use the simulator in their CI setups so that they can test their CUDA code on CPU only nodes, which is an interesting use of it as well. This slide just highlights a couple of the other limitations of the simulator, mainly that it only supports one GPU and one kernel call at a time. You can't use most of the driver API, and a reminder, it is quite slow. So if you wanted to use the simulator with your own code, you set an environment variable to enable it. You then probably wouldn't be able to run with the same size data that you run with an actual GPU. You need to use a much smaller data set or strip down your code to some minimal reproducer so you can get to your problem much more quickly. Then you can run, see if any exceptions occur, and you could maybe import the debugger at certain points and set a breakpoint there. What I have found is that if you try to start things straight off in the Python debugger, it doesn't necessarily work well, I think because of the OS threads implementing CUDA threads, the debugger gets a bit confused. So if you want to break, you have to use, you have to add a breakpoint manually in your code somewhere. So this is, the same example continued using the CUDA simulator. If you were to run it with Numba enable CUDA sim, then you would get this index error, which is like a standard Python exception. If you then wanted to see what was going on, so we see that it's thread 10. You might then conditionally, if you are thread 10, set the breakpoint to break then. Okay. Another example of an error that you might see when you use the simulator, if you've got a division by 0, you could catch that. So this is just an example of a backtrace where somehow a division by 0 occurred. It will give you the example, sorry, the ID of the thread and block in which that occurred. Oh yeah, you can also have Numba generate line info for kernels so that you can profile them using NSIGHT compute and then correlate what you see back to the Python source. So this screenshot shows an example where we've got some Python source on the left, and then we can see things like the number of live registers and the number of instructions that are get executed per Python source line. And then we can correlate those lines with the SAS code as well. That pretty much brings me to the end of all the material that I thought I could cover. Also to show some, some of the interesting use cases in the CUDA Python ecosystem that I've come across, and how you can use CUDA tooling in conjunction with Numba. If you wanted to get started with Numba and try it out, if you're using Anaconda Python, you can install Numba with it, or you can install it with pip. The other thing is, if you don't have a Python environment set up locally and you want to give this a try, you can use Google Colab instead to try it out really quickly. Thank you. If you want to try it out in Colab, then you go to this URL, colab.research.google.com. So I'm hopefully, if I can get out of the presentation, if we head over there. Try and just collect my thoughts again. So Colab allows you to execute a Jupyter notebook, which is a sort of way of interspersing code and text. The good thing about Colab is that you can get access to a node with a GPU for free. So once you've opened a notebook, if you go to runtime and change runtime type, and then you set hardware accelerated to GPU, we'll save that. If I start executing the cells in the notebook, which you can do by clicking play, first of all, there's a warning, like, do you want to run this? I'm going to run it. In this notebook that accompanies the talk, I've got, first of all, just a little bit of code that just uses Numba on the CPU target that runs when everything gets started up, so we can verify that everything's working okay. If you run that cell, you should just see a Mandelbrot. If we carry on running cells, there's a CPU performance benchmark, but I'll skip over that for now. If we go a little bit further, the first CUDA relevant part, there are some instructions on the notebook as well, which you'll be able to see if you're viewing it on GitHub. Anyway, the first cell, import CUDA, is the first relevant one for CUDA, sorry. This is just something for displaying the diagrams in line. What I tend to do on Colab is print the Numba version just to see what version I've got. So the version that you get in a Colab environment is a few releases out of date. We're on 0.5 0.5 at the moment, and you get 0.51 on Colab, which, although it's a few releases old, it's absolutely fine just for getting started with CUDA. The next thing I'd normally want to do on Colab is run CUDA.detect, which is a number function that tells you what you get, what GPUs you've got. So on Colab, it tends to be either Tesla T4s or K80, Tesla K80s that you get. Most of the time I find I get a K80, but this time I've got lucky and I've got a Tesla T4. In terms of CPUs, you can check what CPU you get as well. I normally get a dual core machine. So for the rest of the demo notebook, the code, let me just generate the initial conditions. The idea is I've got 3 versions of a code that simulates some diffusion of some tracer throughout many time steps. So this just generates the initial conditions, and we see that the concentration is highest in the middle. The first version is a Python implementation of the smoothing function. Again, I'm not going to go too deep into what the code's doing, but what I'll mention about the Python version is that it takes so long to run that I've got the code to run it commented out at the moment. You could run it, but I think it would probably take about 10 minutes. So we'll skip that. Further down the notebook is a CUDA-GDB version of the same function, which has some explanation of the... Oh, okay, so for some reason I've lost the runtime. So I'll come back to run this in a minute when I finish talking. Oh yeah, so the notebook it contains some explanation of the changes that were made to run it on CUDA, and the code itself. So what I'm going to have to do, I'm just going to try and reconnect to the runtime and run the rest. In fact, no, what I'm going to do is I'm going to go to a version of the notebook that is pre-recorded with the output so that I don't have to rely on Colab working or not working. So this is the same, but it's a run that I did earlier on my machine. So I'll make this font a little bigger again, I think. So there we are. I had the initial conditions, the Python version, the CPU-GDB version, which after some running, the output is some slightly diffused tracer. I had the CUDA-GDB version as well, which when run produces hopefully the same output. I've got a little sanity check in the notebook just to check that the difference between the CPU and the CUDA solution appears to be pretty much 0. And then a quick, more thorough comparison of the results and some reporting of the execution time as well. So in this case, CUDA was 10 times faster than the CPU. This is the output that we would have seen in the Colab notebook had it not somehow disconnected for me. You can launch this notebook on Colab using the same steps yourself. But what I was aiming to demonstrate there was just how you can sort of quickly try out Numba in the browser if you like, even with the CUDA target. I'm just going to pop back to the slides again. I can get that to pop up. Yeah, so once you've started looking at that, the link to the repository, I think George has already shared it, but it's on the slides. If you make a start with that, and then you want to know a bit more in detail how to use the CUDA target, the official kind of CUDA Numba tutorial is a really good thing to follow. It's in about 5 parts, and it's fairly exhaustive, so you should be able to find out about most areas from it. I'm also going to be talking at GTC on how to use Numba to provide your own compiler for user-defined functions in a CUDA-accelerated application. That's pretty much the end of all my material. I'll come back to that question about typing in a moment, and I'll open up for any other questions as well. Thank you for joining me and listening to me.